Okay, so let's look at another example and see how we can do this. Say I had the following graph here. We have A, and we have B, C, D, we have C in the middle, we have E, okay, and then we have F and G. Okay, let's go ahead and put some edges between them. So we'll have A to B. Let's see, the cost is 1. We'll pick different color actually. Let's connect them first. Okay, D goes to C. D goes to E. D goes to F. Maybe we have D going to G. And maybe we'll put one more edge here. There we go. Let's go now and put some weights on here. We'll have 1, and then we're going to have 1. Let's put one more edge. I forgot to put one more in over here. And we'll have 2, 4, 5, 2. Put one more edge maybe here. That'll be 2. And then we have maybe some more 2s to put one more edge here. That will be cost of 2. Let's say we did everything. Let's make that 3. Okay. So now the question is, which edge do I pick first? And one way to think about it is always pick the cheapest edge first, and we can guarantee that that edge is going to be in the spanning tree. So we can say pick the cheapest edge first. We can prove that the cheapest edge is always going to be in a minimum spanning tree. Okay, and let's see how we can do this. Suppose I have some 2 nodes A and B. Okay, and they are connected through other nodes in the graph, right? So there's some other nodes in a graph. And let's suppose the cheapest edge between A and B is right here in the blue, right? So this is the graph that we have. Let's say this is the cheapest edge here. And let's try to prove this by contradiction. Let us say, suppose, we'll call this edge number 1, edge 1, or let's call edge AB. We'll say edge AB is not in the minimum spanning tree. Okay, that means there is another minimum spanning tree where AB is not in it. So this leads to then there must be a spanning tree, a minimum spanning tree that does not include AB. So let's say the cost of that other spanning tree, we call other minimum spanning tree, and we'll say other minimum spanning tree, and the cost of some that other spanning tree is, we'll call it W. Okay, so certain cost. Now, what does that tell us? That tells us we don't have a cycle, right? And it means that all the vertices between A and B are connected. So the green that we have here, okay, this is a spanning tree, right? Because there's no cycles and it connects all the vertices A and B. And the cost of that spanning tree is W. Now, let's make another spanning tree by introducing the minimum edge. So if I go ahead and introduce the minimum edge here, this was the minimum edge in the tree, that means I would have created a cycle. So if I create a cycle and I want to make it a minimum spanning tree, I have to eliminate one edge. So by adding the cheapest edge, I have to go ahead and I have to remove some other edge. And now we have a new spanning tree, a new spanning tree, right? Now, let's see what the cost of this new minimum spanning tree is. Okay, we said the edge AB is the cheapest. So we said that AB is the cheapest. What does that mean for every other edge in the tree? So all the other edges that I have in the tree, for example, the edge between A and this node here, or the edge between this node and this node, or the edge between this node and this node. All of these different edges that I've highlighted, they're more expensive than AB. Right? So that means I had the original weight W. I've added the cost of AB, and I've removed some edge that is more expensive. Than AB. So for example, if AB costs 2, some edge that is more expensive than AB, it has to be 2 or at least 2 or more, so maybe it's 3. So by adding AB and removing some other edge, the cost will always go down. Okay? Because we removed some other edge that was in the minimum spanning tree before and replaced it with AB. But AB is cheaper than that edge that we removed, so AB must be in the minimum spanning tree. Okay, let me repeat that again. We said that we had some, let's say AB is not in the minimum spanning tree. That means we have another spanning tree that is the cheapest one. And I highlighted that cheapest spanning tree in light green here. And then I said, well, then I'm going to introduce the edge back in, and I'm going to remove another edge that was in the tree. Okay? And then I said, well, what do I get now? Well, since AB was cheaper, okay, that means the weight would have gone down. So therefore, we can conclude that the cheapest spanning tree has to include the cheapest edge. Okay, so there are two ways to use this fact, and depending on which way we choose, we can either end up with Prim's algorithm or we can end up with Kruskal's. Okay, I'm gonna do Prim's algorithm first, and then we're gonna do Kruskal's afterwards. So what I'm gonna do is I'm gonna start an arbitrary node. So let me go ahead and pick the node A. And I'm gonna be doing exactly what I was doing in Dexter's algorithm, but I'm gonna simplify it a little bit. So the first thing I'm gonna do is I'm gonna look at all of the, I pick a node first, right? And then I'm gonna look at all of the edges that are coming out of the node that I picked, and I picked the cheapest one. So I in this case I can pick either AD or AB. Let's go ahead and say I can pick AD, right? And now I pick, so let me get rid of the previous. Here, we'll do this. Okay, so now I pick D. So we have this. And now I keep doing the same thing. I pick the cheapest edge out of A and D. So the cheapest switch out of A and D is now A to B. Okay, so there we go. So currently my cost so far is 1, and then I have 1 here. Okay, and then I keep doing this. So I always pick the cheapest edge out of the nodes that I already have. So if you guys, this is what I have now. If you guys remember to what we did in Dexter's algorithm, we were keeping track of the total cost to each node. And in this case, we're not keeping track of the total cost to each node. We're just keeping track of the total cost of all the edges that we pick. And we always pick the cheapest edge. Okay, so now let's see what my other option that I can pick now. I can pick 2. I can pick this guy. I have a lot of choices. I can pick this. I can pick this. I think I forgot one edge that we don't have the cost there, and that is the D going to E. We forgot to put that in there. Let's go ahead and quickly. There we go. Okay, so and then I have this. So I have all the options that I can take are highlighted in green. So I'm just going to go ahead and pick an arbitrary 2 because there's nothing less than 2. So maybe we'll pick this here. So right now this 2 will be in our cost. So we'll do this and we'll go ahead and highlight it. Oops. There we go. All right, so now let's see what's our next option. Our next option is going to be this 2 here, right? Because we are coming out of G. We have G in here. That's about it. So let's pick our next cheapest option. So maybe I'll just keep going this way, right? And now we'll have 2 as part of the cost. Now F is in our what we've explored, so you have to be careful now. You don't pick edges that already go into the from yellow to yellow. You don't pick edges that connect things that we have explored. So technically we're not going to look at this because our this is how it looks like. Okay, so this is all stuff that we already have. Okay, so I'll pick the next 2. Maybe I'll pick this one here. Okay, so now we have this as part of our tree, and I think we have almost everything connected besides C. So let's go ahead and pick one edge for C. Maybe we'll pick this one, and now I have this edge here. Okay, so my final minimum spanning tree, let's see the total cost. is going to be 1 plus 1 plus 2 plus 2 plus 2. Is that all we got? Let's see. 1 plus 1 is 2. 2 plus 2 is 4. 4, 6, 8, 10. I think I thought it was 9, but I guess I was wrong. So the cheapest way, the cheapest cost is 10. Okay, so my final now spanning tree will look like this: A, D, let's see, B, C, E, we have F, and we have G. Okay, and then our edges are going to be A to D, D to G, G to F. We have A to B, A to E, and we got E to C, and we got all of them connected. Okay, so we always pick the cheapest edge, and that's how we end up with the minimum spanning tree. We just have to make sure that we don't pick an edge that will introduce a cycle, right? Or an edge that wouldn't connect two of the vertices that are already things that we have connected. Okay, so similarly to what I did in when we were talking about Dextra, there are different ways to doing this. The notes show you how to do this with a table. You could also do it with sets, but I'll give you a general idea, and then you can decide which way you like better. One could represent this with just 2 sets. So I could have one set of let's make this yellow, of all of the vertices that we have connected, and then I can have another set that is all of the vertices that we haven't included. That are not connected. Okay, so initially I will list all of the vertices in here. So I'll say A, B, C, D, E, F, and G. Okay, and then I said I was going to pick one vertex at arbitrary, and we're going to put it in this set here, A. Okay, and now we're going to explore at all of the edges that are leading out of A, right? So we'll say for all of the edges that lead out of A, check for the destinations that are in the green set that haven't been explored yet, right? So in this case we'll have A going to D, so A will include D, and then A goes to B, right? And then we have A goes to C. Okay, and the cheapest way, now we figured out, okay, what is the cost of each of these edges? So we have A to B is 1, A to D is 1, and A to C is 2. Okay, so now we're going to go ahead and pick B, because that's the cheapest one. So we're going to take B, right? We're going to put it in this set here, all right? And we'll say the cost to get to B is 1, right? Or the total cost, we'll keep track of. The edge that we've included is 1 so far. Okay, so let's go ahead and maybe mark this with a different color here. right? And at this time, I'm going to go ahead, like we did in Dexter's algorithm, we're going to go ahead and update the cost of how much it takes to get to C from A. So in that case, it takes 2, and then to get from A to D, it takes 1. All right, so now I can keep these green lines here, or I can erase them, but you guys get the idea now. Now I have more options to pick from, because now B goes places. So B goes to C for 3. So in this case, B goes to C for 3, but I can see that I can connect C for only of a cost of 2. So there is no need for me to update this 2 here to a 3, because I can already I can connect C to my spanning tree through A, right? So the yellow here, all the nodes in yellow that I have right here are the nodes currently in my spanning tree. So I can add C to my spanning tree for only of cost of 2. All right, so why would I connect it with a from B, right? So I'm not going to update the cost to get to C. So I can kind of, erase that edge there. Okay, so B can get to E now. I have B to E, and let's say E has no cost yet, so we're going to go ahead and update that to 2. Okay, and B goes, that's it. So what's the next one that we're going to pick? You guys guessed it. We're going to pick D, right? We're going to pick D, because that's the cheapest thing that we can add next to our spanning tree. So now D will end up being in our D, and we can get to D with a cost of 1. So now we have plus 1 here. Okay, now we remove D from here. I'm gonna kind of erase these edges, but you guys get the idea, right? The reason why I always go from the yellow set to the green set, so we go from here to here, is because if I end up going to an edge that's in the yellow, I will introduce a cycle, right? So maybe B and D are connected, but if I look at that edge, that will introduce a cycle, and I'm creating a tree, right? So you can do this with 2 sets like this, or you can do it with a table. Just 2 different approaches how you want to go about it, and you keep doing this until you get all of the nodes from the green set into the yellow set. Okay, so picking the cheapest edge in this approach and adding the cost until you have all nodes connected is Prim's algorithm. Okay, so that's Prim's algorithm. Okay, I hope this made sense.